Hello, AP Physics 1 students. This video is about interpreting graphs of position, velocity, and acceleration versus time, and also, most importantly, relating graphs of position versus time, velocity versus time, and acceleration versus time to each other. So to start, let's imagine we have two objects. One object, which I'll call the red object, has a position versus time graph that looks like this, and another object, which I will creatively call the blue object, has a position versus time graph that looks like this. Okay, so there are two questions that I'm going to pose, and I'm going to show you how you could use this graph to answer those two questions. So the first question is, at what time do the two objects have the same position? And then number two is, at what time do they have the same velocity? All righty. So these are graphs of position versus time, and that's the first thing to recognize, what kind of graph you're actually dealing with. The second thing to appreciate is just roughly what these two objects are doing. The red object over here starts at a positive x coordinate. So the red object starts to the right of the origin, to the right of x equals 0, and it's moving increasingly to the right. It gets a bigger and bigger positive x coordinate over time. The fact that the position is increasing at a constant rate, the fact that the slope of this position versus time graph is constant, means that the velocity is constant. So the red object has a constant velocity, and I know that because its position is increasing at a constant rate, changing at a constant rate. The blue object here starts at a negative x coordinate. So the blue object starts to the left of x equals 0. But eventually it reaches the origin and then blasts right by to bigger and bigger positive x coordinates. And I see that the rate at which the position is changing for the blue object is not constant. This position versus time graph is not linear. So I know that the blue object is accelerating. Okay, so we have a constant velocity object and an accelerating object, just to appreciate that. So at what time do the two objects have the same position? Well, the two objects have the same position when their x values are the same, where their x coordinates are the same. I think you can see that occurs at this point on the graph. So both objects have the same positive x coordinate at this particular time. This time that I'm indicating on the t-axis here is the time at which they have the same x, the same position value. And if you wanted to know what that position value was, you could go across and read off how many meters. If the vertical axis were labeled, you could read off how many meters to the right of the origin the objects are at that particular time. All right, so where the graphs intersect, that is the time when the objects are at the same place. Now, at what time do they have the same velocity? Velocity is the rate at which the position changes. It's the slope of these position versus time graphs. So we're looking for the location, for the time, when I should say, both position versus time graphs have the same slope. The slope of the red object's position versus time graph is a constant positive value. But look, the slope of the blue object's position versus time graph, the slope starts at 0, then the slope gets bigger, more positive, a bigger positive number, a bigger positive number, a bigger positive number. And there is some time where the slope of the blue graph matches that of the red. Now, just eyeballing it, it looks to me like that happens somewhere around there. It looks like a small tangent line that I draw to the blue graph has the same slope as the red graph, roughly at this time. So that's the time where the two objects have the same velocity. And I'm identifying that because both graphs have the same slope. So that answers the two questions. One more thing to point out is the following. Let me change the color here. Okay. So notice at t equals 0, the blue object is at a negative x coordinate and the red object is at a positive x coordinate. So the red object is much further to the right there than the blue object is. And the red object has a bigger x coordinate, meaning it's further to the right than the blue object, up to this time, up to the time at which the objects are at the same location. And then after that, the blue object's x coordinate becomes bigger than the red object's x coordinate. So how do we make sense of it? I'm imagining the red object on the x-axis to the right of the origin, the blue object to the left, and the red object is moving at a constant velocity to the right. The blue object is moving faster and faster to the right. So there is some time. Use some props. It's not red, it's orange, but there's some time at which the blue object is moving just as fast as the red object. That is this time. Okay, that is this time. Long before the blue object is in the same place as the red object, the blue object had to match the speed, the velocity of the red object. And then it had to move faster than the red object in order to actually gain ground. So initially, the blue object is moving slower than the red object, and actually the gap between those two position versus time graphs vertically is growing. But at the time that is circled in green, the blue object has matched the velocity of the red object. And from there on out, it's going to close the gap until a later time at which the objects have the same position. And then the blue object will be in front, further to the right, relative to the red object. So just to highlight that, the red object is gaining ground on the blue object. This gap is widening up to this time, after which the blue object is moving faster than the red object. Now the gap is shortening. Finally, the blue object reaches the red object, and it's moving much, much faster than the red object at that time. The slope of the blue graph is much bigger than the slope of the red graph at the time that they meet up. And from there on out, the blue graph blasts ahead and moves further and further in front. Okay. What if we had some velocity versus time graphs? So suppose the red object's graph looks like this, and the blue object's graph looks like this. Oh, that is red. The blue object's graph looks like this. Okay, and just like before, there are, whoops, where did my whiteboard go? The whiteboard disappeared. Let me try to retrieve that. I really hope this is recording properly. We will find out. Okay. So, what are these graphs telling me? Well, the red object starts out with a positive velocity, right? So the red object is moving to the right. Then it has a smaller positive velocity. So it's still moving to the right, but slower. And then the red object comes to rest. The velocity is 0. Then the red object is moving slowly to the left, faster to the left, faster to the left with an even more dramatically negative velocity. So this red object is moving to the right, slows down, stops, and starts moving faster and faster to the left. The blue object starts with a big negative velocity. It's moving fast to the left. Then it has a smaller negative velocity. It's slowing down. A smaller negative velocity. It's slowing down. Now the blue object has a velocity of 0. It comes to rest. And then it's moving faster and faster in the positive direction to the right. So this blue object, again, is moving left to start, and the red object is moving to the right to start. And maybe the situation looks something like this. They both stop, turn around, and zip by. Or maybe it looks like this. They both stop, turn around, and zip by. I actually don't know if they cross each other, because the situation could look like this. It could look like this. They cross, and then they cross again. Or it could look like this. They never cross, and then they only cross once, or something like that. So here are the two questions. Actually, yeah, here are the two questions. Same questions as before, in fact. So at what time do they have the same position? At what time do they have the same velocity? Well, they have the same, the velocity is the easier question to answer when they have the same velocity, because this is a couple of velocity versus time graphs I'm looking at. So these objects have the same velocity when their velocity versus time graphs intersect. At this time, they have the same velocity at that time. At what time do they have the same position? Well, as I just showed you, I don't really know if the situation, looks like this, turn around and then cross again, or if it looks like this, they never interact at all. I actually don't know anything about the position here. So we don't know if the objects ever have the same position. A graph of position versus time, which is the first graph we looked at today, gives you information about position, and through the slope of that graph gives you information about velocity. A graph of velocity versus time obviously gives you information about the velocity of the object or objects at different times, but it doesn't quite give you precise information about the position of objects. You should view these velocity versus time graphs simply as information about how fast the objects are each moving and in what direction they're moving. But I don't know what the positions of these objects are. These objects might be close together, like the two dry erase markers, or the red object might be in New York and the blue object is in Los Angeles. Information about the velocity of objects alone doesn't tell me where the objects are relative to each other, or if they're ever in the same place. The objects could be in totally different galaxies for all I know. So we don't know if they ever have the same position. We don't know where the objects are located. We just know individually how fast they're moving and in what direction. Right away, we see there's a little asymmetry here. I'd much rather have a position versus time graph. That will give me a much fuller picture of what's going on relative to a velocity versus time graph, which gives me slightly less information. And an acceleration versus time graph would also give me less information, but we'll get to that in the future. All right, so that's a little review of how to interpret position versus time graphs and velocity versus time graphs. But how do we relate these graphs to each other for an individual, like particular object? So I have a group of graphs here, which are position, velocity, and acceleration versus time. And I'm going to make these graphs all consistent with each other. So they all represent the kinematic quantity for the same object and the same situation. Whenever I draw these graphs, I always stack them on top of each other like this. That has the benefit of me being able to look at a particular time and see what the position, velocity, and acceleration look like at that particular time, just by kind of drawing a vertical line. All right, let's have some numerical values here. Let's say the initial position is 10 meters. So the object starts at x equals 10 meters to the right of the origin. Suppose the initial velocity is 8 meters per second. So the object is initially moving to the right at 8 meters per second. And suppose the acceleration is negative 2 meters per second squared. So the object is accelerating to the left at a constant rate of 2 meters per second squared to the left. I'm going to draw this, kind of draw a little diagram of what's happening here. This is my x-axis, where positions are measured in meters. This is the origin, and this object starts at 10. X equals 10 meters. So there's the object. It's got an initial velocity of 8 meters per second, positive 8 meters per second, which means 8 meters per second to the right. And it's got an acceleration of negative 2 meters per second squared, which means 2 meters per second squared, and the arrow shows me to the left. So what you should be picturing is this object is moving to the right, but accelerating to the left. So it's like the wind is blowing it to the left. So it's moving to the right, but accelerating to the left, which causes it to slow down, stop, and then shoot off to the left faster and faster and faster. That's what's going to happen. What do these graphs look like? For the acceleration graph, it's just going to be a flat line. The acceleration has a value of negative 2 meters per second squared throughout this entire process. So that's the easiest graph to construct quickly. Constant negative 2 meters per second squared acceleration value. The velocity graph is not much more difficult to construct. The initial velocity is positive 8 meters per second. And I know the velocity is going to go to 0 as the object slows down, and the velocity is going to become increasingly negative as the object shoots off to the right. The rate at which the velocity changes is just the acceleration, which is a constant negative 2 meters per second squared. So although the object starts out moving at 8 meters per second to the right, 1 second later, it's going to be moving at just 6 meters per second to the right. 1 second later, just 4 meters per second to the right, and 2 meters per second to the right. Then it'll be at rest. Then it'll be moving at negative 2 meters per second velocity, meaning 2 meters per second to the left. And so we have the velocity transitioning from a positive value to a smaller positive value to 0 to a bigger negative value, and so on and so forth. And the position versus time graph, well, the object starts at 10 meters. Initially, the object's moving to the right, so its position is going to become more positive initially. But at some time, the position must stop increasing and become increasingly negative as the object blows right by the origin and shoots off to the left forever. Okay, so let's see how these graphs are related to each other. We start out with a small positive, well, not a small, a big positive slope to this graph. The position versus time graph has a big positive slope to start, which means the position is changing rapidly. Then the slope of the position versus time graph, it's still positive, but it's a little less dramatic. It's a little smaller. At this time, the slope of the position versus time graph flatlines, meaning temporarily the object is not moving further to the right or moving to the left. It's just at rest for a moment. The position versus time graph then has a small negative slope, a larger negative slope, and a much larger negative slope. And the slope of the position versus time graph is just the rate at which the position is changing. That means it is just the velocity value. If I were to draw a little triangle here and calculate the slope of that little tangent line that I drew to the graph, that slope value would be 8 meters per second. The slope would have a value of 8 meters per second. The slope here is 0, which corresponds to a slope value of 0 meters per second. The velocity is 0 meters per second. Here we have a negative slope, and that corresponds down below to a negative velocity value. So what is the takeaway here? I'll tell you. At any time t, the slope of the position versus time graph is the value of the velocity. At any time t, just look at the slope of the position versus time graph, and that slope is numerically the number of meters per second corresponding to the velocity, the rate at which the position of the object is changing. Okay, we can also draw a connection here. The slope of the velocity versus time graph happens to be constant here. The slope has a value of -2 meters per second squared. And I see that that is the value of the acceleration. The value of the acceleration is a constant -2 meters per second squared. So I can write down an additional thing, which is an additional statement, which is at any time t, the slope of the velocity versus time graph is the value of the acceleration. And this is why I always draw the graphs in this order, from top to bottom: position, velocity, and acceleration. If I want to go, so to speak, meaning if I want to do my analysis by going from the top graph to the graph below it to the graph below it, I just look at the slope of a particular graph, and that's going to correspond to the vertically plotted value, whatever the graph beneath it represents. This is easiest to see with the velocity and acceleration graphs. At any time t I choose, the slope of the velocity graph has a value of -2 meters per second squared, and the straight up value of the acceleration is -2 meters per second squared. All right, I've lost the whiteboard again, so I'm going to try to bring it back. So just take a moment. I don't know what's with my computer today, but hopefully these images that I'm referring to are actually appearing in the video. Just have to wait for this to load. All right, one thing I should mention is this concept of slopes corresponding to values in the graph below are valid at particular times. So it's intrinsically about the slope of position versus time corresponding to the instantaneous velocity of the object at that time, and the slope of the velocity versus time graph corresponding to the instantaneous value of the acceleration at that time. This is intrinsically about moments in time and what's instantaneously going on at those moments. Now, suppose we want to go the other way. Suppose we want to go from information about acceleration to information about velocity to information about position. So to make things a little easier, actually, let's start by looking at a very simple graph of velocity versus time. So I'm going to draw one of the simplest velocity versus time graphs I can think of, and it will look like this. Okay, and suppose the velocity has a value of 3 meters per second. So I'm picturing an object that is moving to the right in the positive direction at a steady 3 meters per second. Now, we previously discussed that without additional information, we have no idea like where this object is actually located. I don't know if the object is in New York. I don't know if the object is in Paris. I just know that wherever the object happens to be located, whatever its position is, it's moving to the right at a steady 3 meters per second. Well, if I were to ask the question like, where is the object located at time equals 4 seconds? That's an unanswerable question because we just don't have that information. But suppose I ask the following question instead. Suppose I ask, what is the displacement of the object between 2 seconds and 6 seconds? I'm not asking where it is. Could be in Paris, could be in New York. I am asking how far and in which direction did it move from its starting point at 2 seconds by the time 6 seconds arrived? Okay, this is a question we actually know how to answer, and the graph need not have anything to do with how we go about doing this. I know that the average velocity of an object is defined as the change in position over the change in time. Therefore, the change in position, solving for delta x, the change in position is just the average velocity times the change in time. So the displacement of the object is just its velocity, its average velocity over a time interval times the delta t, the length, the duration of that time interval. In this case, the average velocity is just 3 meters per second, which is the same as the instantaneous velocity at any moment. And the time interval, well, we're going from 2 seconds to t equals 6 seconds. So the time interval is 4 seconds. Multiplying 3 meters per second times 4 seconds, the seconds cancel out. And I just end up with 12 meters. So the displacement is 12 meters. I don't know where the object is located at the end of this interval, where it was at t equals 2 seconds, where the object was at t equals 0 seconds. I don't know. But I know that the displacement between t equals 2 and t equals 6 seconds is 12 meters to the right. Okay. And in fact, I should write it down like this. 12 meters, comma, right is the way to report the displacement of an object. You always have to give the direction explicitly. If we look at the graph, there is a geometric correlation between this answer, 12 meters, and something about this graph. Consider the following. Look at the area trapped between the velocity graph and the time axis, and also between vertical lines that I'm plotting at 2 seconds and 6 seconds. I'm going to call this the area under the velocity versus time graph from 2 seconds to 6 seconds. But it's really the area trapped between, what does that mean? It means it's the area trapped between the velocity plot and the time axis. All right, this area over here is not an ordinary area. It doesn't have units of like centimeters squared or square meters or something like that. It's a bit more of an abstract area. This area has a width, not measured in meters or centimeters, but a width measured in seconds. The width of this abstract rectangle is 4 seconds. The height, or the length, if you will, of this abstract rectangle is 3 meters per second. That's how tall the rectangle is. So this rectangle has some area, and notice that the area is equal to the height times the width, where the height and the width have the units that I'm plotting on the horizontal and vertical axis. Well, this is just 12 meters, of course. Don't know why my whiteboard keeps disappearing. I don't even know if it's disappearing on your end, but it's very frustrating. It's disappearing on my end. If you ever wonder what your future teacher looks like when he's frustrated, you're getting it right now. This is the maximum level of frustration that I that I display. So you have no need to be scared of me in class, unless I'm giving you really intense, serious vibes right now, and you're like, "Oh my God, I don't know if I can deal with this guy for a whole year." But this is my emotional dysregulation. Whatever you're seeing right now doesn't get worse. Um, okay, so the area is 12 meters. It's easy to see in this situation why that's the case, right? Like if displacement is average velocity times time, then it just clearly is the case that the area under that graph is velocity, height, times time interval, which is the width, and that is 12 meters per second. The interesting thing is this is true no matter what the velocity graph looks like. I'm making a bold claim here, whatever the velocity graph looks like, the area under it is equal to the displacement. So I'm going to write this down. The area, I'm going to put this in quotes, the area under a graph of velocity versus time for a time interval, delta t, in this case, delta t equals 4 seconds, is the displacement of the object during that time interval. The area under a graph of velocity versus time for a time interval is the displacement of the object during that time interval. This works even if the velocity is negative. I want to show you that now. So even if the velocity value were negative, it would still be true that the area under the velocity versus time graph represents the displacement of the object between before a time interval, during a time interval. For instance, suppose the velocity versus time value were negative, let's see, negative 6 meters per second. And suppose further that we're interested in the time interval from 1 second to 5 seconds. Well, the displacement of the object between 1 second and 5 seconds is just going to be the average velocity, which in this case is easy to identify. It's negative 6 meters per second. This object is moving to the left at 6 meters per second, times the time interval between 1 and 5 seconds. It's again a 4-second time interval. And this gives us, after we cancel out the units of seconds, negative 24 meters. So the displacement is 24 meters to the left. Okay. And what if we inspect what's going on from an area's point of view? Well, the area under this velocity versus time graph should always be interpreted as the area trapped between the plot and the t-axis, the time axis. So the width of this rectangle is 4 seconds, and I'm going to interpret the height as being negative 6 meters per second. This rectangle has an area, and the area is just the product of that negative height of negative 6 meters per second times the width, which is always positive, 4 seconds. There's negative 24 meters. So it works. If the velocity were more negative, let's say this red line were even further down, then the area would be much bigger. And that makes sense because the leftward negative displacement would also be much bigger. Again, I'm not proving that this works for any shape graph. I'm stating that it works for any graph. A formal proof of this would fall under the category of the subject of integral calculus. So if you took calculus last year, or you're taking calculus now, you have or shortly will be looking at things called derivatives, which are simply the slopes that we talked about in the previous section, and also integrals, which correspond to areas underneath of graphs and how they relate to other quantities. Just to give you an idea of what some graphs might look like that you have to deal with. I can imagine having a velocity versus time graph that looks something like this. Okay, kind of weird looking, right? So how would I handle a situation like this? Suppose I'm interested in the displacement of the object from t equals 0 to some later time t. Well, it looks like I have a triangular area here, so I could compute that pretty easily. And up to here, it looks like I have a rectangular area, which I could compute pretty easily. This additional positive area here would be very difficult to compute, okay? Calculus lets you do this sort of thing if you know what graph you're dealing with, what shape you're dealing with in that red squiggle there. But it would be very difficult to deal with that if you don't know the shape of the graph and if you don't know calculus. In this course, we're going to be dealing with only graphs that can be broken up into geometric areas that you're familiar with, like triangles, trapezoids, rectangles, things like this. And then notice over here, we have this negative area because the velocity is negative. So the object is moving to the right in each of these sections. In each of these sections, the velocity is positive, the area in each interval is positive, the object is advancing to the right. But in this section, the velocity is negative, the area is negative, and the object is moving to the left and backtracking. So you're kind of undoing the positive displacement when you have this negative displacement that kicks in because the object is now moving backwards. All right, I'm going to make another statement here, which is the following. The area under a graph of acceleration versus time is the change in velocity. This must be true because position is related to velocity in the same way that velocity is related to acceleration, right? Velocity is the rate at which position changes. Acceleration is the rate at which velocity changes. And so it must be true that however the position and velocity graphs are related, namely the area under the velocity versus time graph is the change in position, the area under a acceleration versus time graph must give you the change in velocity. Let me just write that down here. Area under velocity versus time equals the displacement, or delta x. And the area under acceleration versus time is equal to the change in velocity, which could be a positive or negative change, depending on what the initial and final velocity values are. To recap, if you are given information about a position graph and want to know what the velocity graph or the velocity values might like to look like, or you're given information about velocity and you want to extract information about acceleration, you're going from top to bottom using slopes. And if you're given information about velocity and want to know what the graph above, the position graph, might look like, or at least you can figure out what the displacement is between any two times, or you're given information about acceleration and you want to find out something about velocity, namely the change in velocity for a time interval, you are using the concept of areas and working from the bottom to the top of those graphs. Okay, I hope this is instructive. This should be familiar to you if you have taken calculus already, but if you haven't, now you're on the same page as everybody else with respect to what you need to know for this course. So until next time, be well.